Hello, my name is Travel Edna Takaisa from Group MLSW24, and today I'm presenting to you the real-time biomechanical skill classification for bike dispatch via cloud-deployed low-short-term memory neural networks. The overview of everything I'm covering today is right here: introduction, problem statement, research contributions, methodology, dataset description, results, video selection, conclusion, acknowledgement. Road accidents involving bike riders has become an increasingly rampant safety concern, especially in Uganda, and this has resulted mostly as a result of the lack of fundamental skills on the road, such as safely navigating from one lane to another, or basically just navigating along a corner. And so our system presents a solution where a demonstration of competence is done before riders are accepted to go on the road, and then this demonstration is recorded and evaluated, and the verdict is given on whether the rider is good or average or rather poor. For the main application problem, that my rider assessment system is basically designed to assess the skill level of a particular rider based off a short video clip that is performed, and the system basically focuses on analyzing the riding behavior of the rider using the video data to evaluate the rider skill and detect any unsafe riding patterns. For the computational problem, it just basically involves automatically analyzing the video data to extract biomechanical features. In this case, we extracted the 7 biomechanical features, which are balance, posture, confidence, speed consistency, upper body stability, pedal rhythm, as well as the pedal consistency, whereby using machine learning techniques, we're able to identify patterns in rider movement that distinguish the skilled riders from the unskilled riders. Basically, just process video frames, extract motion features, and then apply algorithms to group riders based on the similarity in the riding behavior. Our research question is that can unsupervised machine learning reliably differentiate skilled from unskilled riders using only visual biomechanical features? Our objectives were to conduct a comprehensive exploratory data analysis as well as assess the rider skill level using the rider's form. Our contributions and outputs is that we got a rider skill dataset that is the RoboFlow cycling images as well as the ECF101 video forms that were covering the bike riders. We produced a comprehensive visualization exploratory data analysis sheet that systematically validates cluster quality. We built 8 models for our data set with 4 models for each data set, and then we chose the best, which was the LSTM, the long short-term memory neural network, and we deployed it. For our methodology, it was basically problem statement first, identifying that there is a lot of lack of skill by riders, which led to the rampant road accidents in Uganda today. We obtained the 2 data sets and performed an EDA, trained models, deployed our best models, applied compression techniques, and lastly, we deployed the best compressed model. Dataset description, we basically have 2 datasets. That is the ECF101 dataset containing the human action recognition that is focusing on a biking class, containing the videos of the bike riders used to determine the behavior patterns that make the riders to make mistakes. And then we have the RoboFlow dataset, which shows us the still images of cyclists in the road environment. In the datasets, we'll be looking at 7 features. The first one being the balance, which looks at the hip alignment, the posture, which looks at how the torso is aligned with the hip, the confidence, which clearly checks that the post detection algorithm can clearly see the riders within the frames. The speed consistency basically just looks at how consistent the limbs are during the riding process, to say the hands, the knees, as well as the legs. Upper body stability basically looks at the positioning of the shoulders during the riding process. Pedaling rhythm is looking at how consistent the pedaling is over that time. And lastly, the pedaling symmetry just basically looks at how both legs are moving evenly during the riding process. Moving on to the visualizations. In the first upper visualizations, we are basically looking at how the clusters are distributed across both datasets to distinguish clearly between the skilled as well as the unskilled samples. This is after the post detection extraction, after the post-extraction of the samples. So these are the samples we get after the unclear samples in our data sets are removed. So below, we are also looking at the data source contribution, whereby we are looking at how many samples are present within each data set after the media pipe post-extraction, and also how they are clearly distinguishing between the skilled as well as the unskilled for each data set. The split distribution by source, we see how many samples are present within each split of each data set. For the Rockefeller data set, we have basically 3 splits, and for the UCF 101 data set, we have just 1 split. And these are the samples after the media pipe post extraction, which has also been detected, which has also been demonstrated below in the other visualizations. For the detection rate by source as well as the input versus input detected samples, we are basically looking at the number of samples that remain after the media pipe post extraction has been done. And as you can see, our detection rate is quite low. This is basically because our media pipe post extraction happened and all the unclear images as well as videos were dropped, and we only remain with the clear videos. So after the extraction, then the detected samples were relatively low as compared to the input ones. Moving on to the correlations, we are basically looking at how the features are closely correlated amongst each other, and we see that we have a highest correlation between posture and upper body stability, meaning that for the posture of a person or a rider to be good, the upper body stability must also be good, meaning that they should not be swaying their shoulders from side to side unsteadily during the riding process. Here we are basically looking at the features and how, if they can clearly distinguish between the different classes we have. We have 3 classes, which is the poor class, the good class, as well as the average class. And as you can see, we have a very good score for upper body stability and posture, and relatively a bit low scores for the pedal rhythm, balance, as well as the pedal symmetry. But it clearly shows that these are able to distinguish among the 3 classes of the skill tiers that we have. Here, this is the class distribution of sequences extracted from the firms, and this is based on the ECF 101 dataset, and we can clearly see that we have poor and average at 33% each, and then the good at 34%. Then the main feature score by class, we are basically looking at how each feature performs within each class, and as you can see, we relatively have a high score for good across all of them except the speed consistency, as well as average is relatively high for all except for balance as well as speed consistency. For the feature box plots, they also clearly show us that for posture and upper body stability, they are able to clearly distinguish between the 3 classes we have, the poor, the average, and good, as compared to the other features that we have here, which is also being demonstrated in the feature distributions by class that are here. We are going to move on to the models that we created. We trained for the different data sets. This was trained on the ECF 101 dataset, which is the graphical neural network that operates basically on connected nodes. And for this dataset, the human body is basically seen as a graph. So we construct the graph from the videos, and for each of the 16 frames in a clip, MediaPipe just basically gives us 33 joint positions, and each joint just becomes a node carrying 5 values. We achieved a mean accuracy of basically 60.51%. So in the first layer, basically joints talk to the nearest neighbors. Then in the second layers, they talk to each other so that patterns across can emerge. In the third layer, basically we get information about the immediately neighbor from layer 1, and then the joint patterns in layer 2 are grouped and combined into full understanding of the body. In layer 4 is whereby we have the global average pooling that takes the mean across all nodes that produces a single vector, which single vector is then compressed into a summary. And then the summary is narrowed down into 3 possibilities, which is poor, average, as well as good. The third The 3D convolutional neural network basically learns patterns that exist across multiple frames at once by asking what changes are across these frames. So since we have a small data set for the UCF 101 data set, we basically split training taking 80% and the test taking 20%, which means that the test set will have only 27 videos, which are very few for reliable evaluation, so that the data was divided into 5 folds, and the mean accuracy across the 5 folds gave us a mean accuracy of 34.33%, which was relatively low, basically because of the small data set that we got. So layer 1, we basically learn basic motion patterns, edges moving across the frames. Then the joint movement patterns are learned in layer 2. Then we go to body part coordination, that is learned in layer 3. High-level cycling patterns are then learned in layer 4. And then layer 5 just basically combines everything to make one clip summary, which is narrowed down into 3 possibilities, which is good, average, or poor. The support vector machine is basically just works very well with the small data sets. And so with the 7 biomechanical features cohorts, it can find boundaries. In layer 1, we basically just center every feature around 0 and then scale it so that 1 unit equals 1 standard deviation. The RBF, which is a radial basis function, basically projects the data into higher dimensional space where a linear boundary becomes possible, and this is because cycling from data is not linearly separable. Under this, we achieved a mean accuracy of 98.34%. Moving on to K-means, this was done on the RoboFlow dataset, whereby it just basically partitions our data into K clusters by minimizing the within cluster variance, and each sample is then assigned to the nearest centroid, and the centroids are updated iteratively until the convergence happens. This model is very simple and fast, but assumes spherical equal-size clusters, which is a limitation when the wider distribution postures are irregular or overlapping. For the DB scan, we are basically grouping points that are closely packed together and mark the isolated points as noise. So it was basically used to detect outlier riding postures and identify the dense skill clusters in post-feature space. For agglomerative clustering, which is also done on the RoboFlow dataset, it is just a bottom-up approach where each data starts as its own cluster, and then the 2 closest clusters are then merged repeatedly until a stopping criterion is met. A result is a dendrogram showing the full merge tree. The Gaussian mixture model basically is a mixture of the K Gaussian distributions fitted by the expectation maximization, and this one basically just captures probabilistic nature of school levels where boundaries between school classes are inherently fuzzy. It is more expressive than the K-means, and it is suited to detecting overlapping posture clusters, but requires choosing K, and it's sensitive to initialization. Our last model, which was performed on the UCF 101 dataset, is the LSTM, which is the long short-term memory neural network, which was our best model. This one understands time by reading 16 frames sequentially and detecting trends like iterating balance, improving rhythm that the CVM cannot see. It just scales better because prediction time stays fixed as training data grows. So it was designed for sequential motion data, which is exactly what cycling analysis requires. We had the input LSTM, drop out the second LSTM out, then the second dropout, the depth as well as the output. Basically, in the first layer, we have the primary memory, whereby the first frame sees the first row, then the second frame sees the second row, but remember the first frame. Then by the 16th frame, we have accumulated the full context of everything that has happened in the frame across the clip. In the second layer, we basically train 30% of the 128 units randomly set to 0, and this makes the model not to rely on one feature, but make it generalized to new and seen videos. In the second LSTM, we're basically receiving all the 16 frames from the first LSTM, which are compressed to form one summary. In the fourth layer, the specific purpose is basically to just help the model make final decision based on the generalized patterns and not on the memorized training samples. Then the fifth layer just takes the summary and converts everything into the 3 possibilities, which are poor, average, and good. And the deploy pipeline, we had the development layer where we had all the code done on our machine, and this is where all the code was done. The model files were quite big, and we stored them on the Git LFS instead of Git. In the second layer, we have the build layer, where we have the Docker file, which defines our environment. And in the third layer, we have the cloud layer, whereby we have two working spaces, the API space, which runs the Docker file, as well as the UI space, which is just a simple static file running on the browser. For the fourth user layer is basically demonstrated here, whereby we put our video in this, then we upload it here, we analyze the writing form, we're able to get a verdict, as well as the score per feature, as well as coaching tips, and the video information, including duration, frames per second, frames, the detected frames, as well as the sequences. Model compression was basically done because our model had very many parameters which were manageable on the server, but were very heavy for the mobile device. So our first one was the knowledge distillation, where we trained a student model using the teacher model. So this was the student model, which was the attention student model. It processes all the frames in the video clip sequentially, and then processes all the model simultaneously. We had about 7 layers of this, whereby we had the dense projection in the first layer, whereby each frame forms 7 features, which are projected onto 32 dimensions. In layer 2, it just lets the frames talk to each other, which can lead to different types of relationships. And after, in layer 3, we add the original input back to the attention input, and the normalization stabilizes the values. In layer 4, basically, we process each frame independently to refine the mixed representations. And layer 5, original input is then added back to the attention output, and layer normalization stabilizes the values. And layer 6, after every frame has been enriched, the layer then collapses the frames into single summary. And in layer 7, we are then narrowing down the summary into the good, average, or poor. Pruning is basically where we remove the redundant low magnitude weights to create a sparse model. We had 3 methods. The first method is the one-shot 50%, where half of all the weights are zeroed in a single pass. There we achieved a smaller file, but then the prediction agreement was very low, 49%. Then the method B, where we had the one-shot 70% of the weights were removed in one pass, giving the smallest file, but then the model lost more signal, and this became not very useful for our project. Moving on to method C, whereby instead of printing everything at once, we just basically moved weights in 5 rounds, and then we were retraining between each round so that the model can recover. The agreement remained at 95%, but then the file only shrunk by 7.9%, which has been demonstrated here in the table. So this was the deployed model after, which was the knowledge distillation, whereby we upload the video here. We're able to analyze, then get the verdict in a time period, and then get coaching tips. So the system successfully differentiates between skilled and unskilled riders based on the 7 biomechanical features, and the posture balance and upper body stability greatly affect the rider movement. Early detection of rider skill can significantly reduce the level of accidents. So our limitations were data set constraints, especially in Uganda, the Ugandan domain, and the results also may vary from the expert cyclist coach. And also there were media purpose detection failures, biased, which were only looking at easier and cleaner samples and leaving the harder and clear samples. So we would like to lastly acknowledge Dr. Galango for his support during this process, giving us the extra time, and also his guidance was very crucial in doing this project. Thank you so much.